Thank you, gentlemen. It's a huge pleasure for me to be here. Thanks, Hussein and Gilad, for inviting me. So yes, I got up early this morning to catch 3 trains to come here. Actually, one was a 2-minute connection, the other one was a 3-minute connection, and they were all on time. So it was just absolutely amazing. So we are in Switzerland. We are live. Be careful. They also left on time, so the bus will not wait for you. I just repeat that here. Okay, so my name is Torsten. I am a professor at ETH Zurich, and this work is actually shared work where I need to credit many people. So many of my group members in the group also, but also Microsoft will show up here as a collaborator, where I spent my sabbatical in 2019 to design some interesting things that I'll be talking about here. But the topic is really network support for high-performance deep learning systems. Well, now the question is, why do we care about this deep learning? It's absolutely ridiculous stuff, isn't it? Like, nobody needs that, really. Well, you may have heard about ChatGPT, and there's an interesting thing that just happened a couple of months ago. So ChatGPT now pretty much passes a lot of tests that humans pass and the average human would not pass, including me. For example, the bar exam. So the MBA exam, I would not pass that. A medical licensing exam, I would also not pass that. And in fact, it would probably earn more money than I make if it would apply at Google to be an engineer. So now the big question is, after all this AI frenzy comes, what is left for us humans? And if you go back and try to find out what's the difference, or what is the differentiating factor in humans, you will actually find something very interesting. So what makes humans unique is one of the things, so let me actually use that laser pointer here. One of the things that makes humans unique is in fact the capability to understand other humans. So that is, in scientific terms, that is the theory of mind. So that is the difference that differentiates us from many animals, including apes. So I can understand what you think to some extent. I can understand how I have a model of you, of most of you. So now the question is, can AI do that? The answer is, unfortunately, already yes. So really, there's not much left for us to do besides making AI more successful. And this is exactly what I want to talk about today. How do we make large-scale AI more successful, and what are the next steps? So actually, much of that follows a very interesting Turing Award lecture 2018 by Geoff Hinton and Jan LeCun. Many of you have probably seen it, but there are 2 things that I want to highlight in this lecture. Hinton says, really the deciding factor for the AI revolution was the increase in compute power. Furthermore, I think a lot of credit to for deep learning goes to the people who made computers go fast. So again, this talk is going to be very performance-centric, but really it is what is fueling the AI revolution as we are seeing it today, much of it also from NVIDIA. And going back to the time when I started my sabbatical at Microsoft, the billion-dollar industry, it was actually 2019, August 2019. I started in June 2019. There's a certain correlation we could speculate about. Greg Brockman, the CTO of OpenAI, said, I think the most benefit will go to whoever has the biggest computer. Now, 2023, we see that is true, because there was quite a big computer involved in building this. So now the question is, how do we make computers go fast? Well, who else do we ask but Jack Dongarra, our community's Turing Award winner, who was able to help accelerate supercomputers to more than 70% dense linear algebra efficiency. So that was really Jack's legacy, and I would claim he drove much of the revolution himself as well. But now going to AI. Supercomputers are really what makes modern AI. And this is quite interesting. So for the first time, I would say in history, large companies are bragging about their supercomputing resources. So there's now a race going on to build larger, faster, better computers in top-level industry. All the mega data center providers build these computers. Facebook has an AI supercomputer. Who would have thought that a company that runs a social network needs a supercomputer to running a social network? Well, I didn't. Tesla, a car company, runs a supercomputer. What? A car company running a supercomputer? They actually built their own supercomputer from scratch, the Dojo machine. They built their own chips, they built their own network, they built their own pretty much everything, software stack, everything. Google has an AI supercomputer. Microsoft pledged $1 billion to create an AI supercomputer. They even have a comic about it. So that's Microsoft's CTO pointing at an AI supercomputer for the masses. So this is something that is really a phase change in industry. And what are these supercomputers for? These supercomputers are mainly for training large language models as we know them today, as ChatGPT, GPT-4, GPT-3, many of you have used them. But how do they work? Well, they work actually by building a so-called foundation model by unsupervised training from basically the internet, clean data from the internet. So you take text from the internet, like this text here, then you omit a word in this text. What you do is you run it through a so-called transformer network. The transformer network is nothing but a function. That function takes the input text and the omitted word, and then outputs a probability distribution of what it guesses the right word could be. In this case, I mean, you can guess yourself. The model is reasonably correct. And then, of course, you know which word you removed from the text. Right? It's pretty obvious. You take a word, you remove it. Of course, you remember what you removed. And then you can train the model to update the model to predict the right word you removed. So this now enables training of basically all of the human data that we have ever created that is in the internet, run them through an AI model, and train that probability distribution of generative language models. The only limit we have is the compute capability, because our internet is pretty big. Nobody today is able to run the whole internet through computers to train these models, but soon we will be. And soon everything we are saying, like including the talk I'm giving right now, I'm 99.999% sure this will at some point go through some deep neural network, some machine will learn from what I'm saying right now, and will be able to repeat it to you. Okay, so how does this work? Well, GPT-3 is the most known one, 500 billion tokens, and soon will be the whole internet. So a token is about a word. It's a word piece, but yeah, let's not get into details here. So then the size of the model itself, GPT-3, has 175 billion parameters, which is 700 gigabyte just in FP32, meaning that no single accelerator can actually hold the whole model, meaning we need the computation network I'm going to talk about in a couple of minutes, and it takes weeks to train. So this was just the introduction. I don't want to go into too much detail on the techniques. There's a whole other talk that I could be giving on this. But really the upshot of that other talk, and if you're interested, you could watch it on YouTube. The upshot of that other talk is really data movement is for that computational problem to really process all the knowledge of humanity most important. So it's basically all about data movement. Especially in the network, as we are scaling up to large machines. So here at the HPC Advisory Council, we care mostly about the network. I was specifically invited to give a keynote about networks. Thus, I will now switch to networks and ignore pretty much everything else. I ignore high-performance I/O, I ignore high-performance compute, but I'm going to focus on high-performance communication. Again, if you want to know about these other aspects of deep learning, you can watch the talk I just referenced. So now, going towards parallel deep learning, what does that mean? So we first need to understand the model. How does it look like? How do we parallelize or distribute a deep learning model? And specifically the deep learning model I talked about, that's the basis of ChatGPT, GPT-3, GPT-4, that's a transformer model. So how does that model work? Well, you train it with lots of text. That's what I mentioned. So we have lots of text. The text is, of course, arranged in sentences, words in sentences, in documents, in web pages, and I don't know what. So we cut this into multiple batches, so-called mini batches. These mini batches are statistical units of training. Again, let's not get into details. If you have any questions, please let me know right away. I'm super happy to be interrupted right away, or you can also ask me in the break. I will unfortunately not be able to make it to the dinner event due to the looming SC deadline on Thursday, so I have to help my team. So there are three forms of parallelism in these deep learning models. The first one, the simplest one, the traditional one, many people say, the first parallelism is data parallelism. What do you do in data parallelism? Well, you take your model, like I mentioned, and by the way, the model is nothing but a computational structure that's parameterized by a lot of trainable weights. As I mentioned, these 175 billion parameters. So you take the model, you copy it through to 3 different machines. So each of these whole thing is a model. So now we have data parallelism of size 3, so we run it on 3 different machines. Of course, now you realize, well, if my model is 700 gigabyte in size, there's no single accelerator that can hold 700 gigabyte parameters. Usually, the largest one that I'm aware of is 80 gigabyte, so you will need at least 10 of those to hold the parameters. Then you have activations as well, so you probably need more like 20 to 25 accelerators minimum of those large configuration to actually run the model. What do? Well, you actually distribute each of these models now to different accelerators. Here in this case, the yellow, the red, and the blue one. So we now distribute the first layer, then the second layer, and then the third layer to 3 different accelerators. Now we are already employing 9 accelerators, 3 times 3. So now you realize, oh, but my model is not very fast. if I'm processing this model on a GPT-3 model at full size in this pipeline parallelism, it's actually not getting faster. It's just enabling it. If I now want to make it faster, I need a third level of parallelism that is called operator parallelism. Now each of these layers needs to run faster, because if I pipeline, it doesn't get faster, obviously. I still process the first layer, then the second, then the third, just on different machines. So it's just to make them fit. If I want to make them faster, I can now cut each operator into 3 different pieces in this case, now employing 27 different accelerators. So that is the final and for this talk, greatest decomposition for these models. Okay, so we have 3 different levels of parallelism. So now let's talk about each of those and how we can work with those in the network. First of all, data parallelism. So data parallelism is quite funny, because data parallelism is really the parallelism where we have 3 different model copies, as I mentioned here, and we just need to make sure that the trained weights are actually the same in those 3 different model copies. So that every single time I'm updating my weights, as I mentioned in the first slide, all of the models get the same update to the weights, such that the weights are actually the same, because otherwise they would diverge. How do you do this in a high-performance computing environment? Does anybody have an idea? Which function would you use? Which MPI function? Oh, come on. Yes?
Maybe Windows.
Windows. Well, you could. Yes, that's true. But commonly there is another function, a collective function. All reduce. It's all about all reduce. It's all about finding a global sum across your, in this case, 3 accelerators. So now there is a very funny observation that you can make in deep learning. So my brain is extremely unreliable. Extremely unreliable. It actually has like a 95% hit rate when it comes to signal processing, so it's super bad. So in deep learning, you can do similar things. You can actually take the unreliability of the overall circuit to some extent that you can drop 90 to 99.9% of the small values in your communication and just not care about them. You can actually sum them later. You can defer them to later. So this is actually quite a cool insight. You can find a full proof down here. I could also present this full proof to you now. It's a wonderful NeurIPS paper by a collaborator of mine, Dan Alistar, and I helped a bit. But actually, I don't want to spend lots of time looking at equations here. You can also look at empirical results. The final result is quite funny. So in this gradient communication, so just looking at this ResNet 10 here, you can actually use only 0.025% of the values. You can only communicate, or it is sufficient to communicate 0.025% of the top K values, and you still get the same convergence, the same error, as you would run in the baseline with 100% communication. So you can actually highly sparsify your gradient communication, and it's still all fine. This is quite an interesting insight. Now, you would need to implement a sparse all reduction. Currently, MPI all reduces dense. It doesn't do anything sparse, which is quite challenging. In fact, we have a bunch of papers on this, how to make this better. So there's a discussion how to make this near optimal. And it's even harder if you talk about in-network all reduce. So for example, things like SHARP that you may hear about or may have heard about, but certainly will hear about at this venue, will have, of course, trouble with sparse all reductions because, well, it's not built for it yet. And this is an interesting extension. But okay, let me not get into much all-reduced detail. Let me now move to the second form of parallelism, pipeline parallelism. So pipeline parallelism is really going from left to right. And let me now redraw this a little bit, because this is a very tricky form of parallelism, going from top to bottom. Here, stage 1 is layer 1, stage 0 is layer 1, stage 1 is layer 2, stage 2 is layer 3, going from top to bottom here, right? So what does this mean if I'm now processing a mini batch, or if I'm now processing an example? I'm going from stage 1 to stage 2 to stage 3 to stage 4. And if I'm training, backpropagation, which is our standard training algorithm, goes backwards, as the name suggests, backpropagate, and it goes the pipeline back from the last accelerator to the previous, to the previous, to the next. And if I'm now processing a single, so this may be customer 1 making a request to ChatGPT and assuming ChatGPT actually learns from your request, customer 2 making a request, and then it learns. But now you would immediately see, well, that's very inefficient. What you would do is you would probably run those at kind of simultaneously down the pipeline. But then you see, well, because of this silly going back up, I have a bubble here. And I have bubbles on the path back, and you only get less than 50% utilization of this thing because of the backpropagation. Bubbling. So what you can now do is you can actually go backwards. You can now say, well, you know, I can run another replica of the model from bottom to top. So actually, accelerator 0 runs the first stage, but accelerator 3 in this case runs also the first stage of another model replica and then goes from bottom to top. So now we go from top to bottom in the first case, and from bottom to top in the second case. And now if you pay attention, you can run these two pipelines actually at the same time. And now you save the pipeline startup and teardown overhead, so you're running a so-called double pipelining scheme in two directions with your set of accelerators. This gets you about a 50% utilization boost. Of course, it's going to be a $1 trillion industry. All of us could get rich by inventing this. So this also works for the more realistic case that the backwards pass takes twice as long as the forward pass. Some of you experts in the audience I've already seen them are smirking at me like, yeah, I know, the backward pass is 2 matrix multiplications. Why are you drawing the same? That is just exactly the same. It's slightly more complicated to explain. So we also benchmarked it on the Pitstein supercomputer. The computer just sits over there, a pretty large machine. And you can see, compared with all other schemes, our scheme, the Chimera scheme, is outcompeting. By the way, there are a lot of pipeline parallelism schemes for deep learning because, as I mentioned, it's a $1 trillion industry. Pretty much everybody is working on that topic. So far, Chimera, until now, is the fastest known scheme with about 40% to, or 16 to 40% speed up with across any other scheme. Again, if you care about the details, by the way, for everything on my talk, you find an archive link up here where you can read details about everything. I'm just giving you a rough overview in this keynote-style presentation that you can see what you're most interested in and then dive deep. The last form of parallelism I want to emphasize here before going into more details on architecture is operator parallelism. So operator parallelism is, again, taking a single layer, cutting it into multiple pieces. So what is a single layer in a deep learning network? Well, it is really mostly matrix multiplication. So in fact, if you just look at a transformer layer here, this is an encoder. This is the thing that answers your ChatGPT query. So that's literally one of the 96 layers of GPT-3. That consists to 99.8% of the flops of matrix multiplication, essentially. Then 0.2% of the flops go to statistical normalization, this is softmax, and some element-wise operations, which is basically GLU and things that don't matter that much. So really 99.8% is matrix multiplication, so let's just focus on that for this talk. By the way, these softmax and element-wise, they cause a little bit of trouble, but you can employ very similar schemes than I'm going to briefly outline here in a minute, and you can handle those as well. So really, the upshot is large matrix multiplies dense today. Dense matrix multiplies dominate large language models. For example, GPT-3, the exact matrix size is 12 to 88 by 12 to 88, so this is a gigantic matrix full of numbers. So this is in FP32, that's just 600 megabyte, right? The parameter matrix, a single parameter matrix is 600 megabyte, and we have 2 of those in each encoder. We have 96 encoders in a GPT-3 model. By the way, you may be asking, why am I talking about GPT-3 and not GPT-4, as Microsoft now announced is the model behind Bing? The numbers are not public there, so I cannot actually tell you the exact sizes. But it's a very similar model. Okay, so really interestingly, if you do inference, you have tall and skinny matrices, so it gets a little bit more complicated on that front even. So what would you now do? Well, you would now basically say, I want to distribute that matrix multiplication. So I need to implement parallel matrix multiplication. There is one of our earlier works which even predates the deep learning frenzy, where we came up with Cosma in deep collaboration with CSCS, by the way. So CSCS is a great partner to work with. I can just emphasize this. In this collaboration, we implemented for a scientific computing code the so far fastest and best communication avoiding matrix multiplication in the West, at least. And so using a partial replication and an outer product schedule, it's quite nice. It was developed for CP2K at the time, but it's also used in deep learning now because it's very much the same computational pattern. I could now give you a couple of proofs why it's optimal and why it's good, but I'll just skip this. By the way, we have been working on another framework in a student thesis, AutoDDL, that combines this parallelism with these the matrix multiply parallelism with these statistical normalization operations that I mentioned earlier. They're a little, as I mentioned, a little bit annoying, but not too hard to handle. If you're familiar with NVIDIA's Megatron LM work, we improve upon that actually quite significantly. So now I've basically given you a crash course on how to parallelize large language models. Right? So now you understand these 3 forms of parallelism: pipeline, data, and operator. You know what each of those do. You would be able to implement a wonderful, fast framework for distributed parallelism. This is This would enable you to build a state-of-the-art framework. But now let's go one step further. Like now you've built that framework, and now you realize, well, you know, it's still a $1 trillion industry. Would I run this on a standard computer? No. Of course, we would be building a network and a computer specifically for that machine. Because if I have $1 trillion at hand to build such a machine, I'm not going to buy an off-the-shelf machine. I'm going to develop a better one. So now let's actually look a little bit more in structure of what these three forms of communication actually give us. So data parallelism, now we have three different copies of the model, as I mentioned. We are running an all-reduce operation on those three different copies of the model, which means this can be implemented by a ring communication. Like all-reduce, large message all-reduce can be implemented by a ring. Pipeline parallelism is, again, we take the same thing, we take a model, and we cut it into pipeline stages. So we are communicating only with the nearest neighbors, forward and backward. Remember, in a ring, I'm also only communicating with the nearest neighbors, forward and backward. The operator parallelism I just mentioned, the matrix multiplication, is now cutting the third dimension. So here, model replica, here, layer parallelism, and here we parallelize each layer. So in this illustration, it's going to parallelize from top to bottom. So we have another all-reduce, or in the case of convolutional neural networks, which I didn't cover, but let's just assume matrix multiplication, we have another all-reduce going up and down. So quite nice. If we now combine these three levels of parallelization, what do we get? Anybody? What is the final overall communication pattern if we take the three-dimensional ring, essentially ring pattern? That is the fundamental insight of the next 10 minutes. Yes? 3D torus. We have a 3D torus, exactly. At the end, if we take all this together, we have a three-dimensional torus. Oh, that's quite nice. Remember this? Communication in deep learning can be shoehorned into a three-dimensional torus if you pay enough attention. So this means we have only very local connectivity. I'm lying a tiny bit, but just bear with me. It's mostly right. So what can we do? Well, the first observation that I made at the very beginning of the talk that I didn't give you because it would take me a 2-hour keynote, and again, you can watch it on YouTube. There's a 1-hour talk on why data movement is so important. But just believe me, network bandwidth and memory bandwidth is the oil in AI supercomputing. Okay, it is. You need more bandwidth than ever. To just give you some, I will give you some data in a minute. So actually, memory bandwidth, I'm not too worried about building accelerators. That's just HBM. HBM will get us a lot of memory bandwidth. Check. SK Hynix will fix it. Samsung will fix it. So these technologies will just come. Network bandwidth is a problem, because network bandwidth is much more complex. It goes much wider. It's much more expensive than memory bandwidth. So if you just look at today's HPC systems, the Slingshot system deployed at CSCS, but also at Frontier, the ALP system will be a Slingshot system, has 200 gigabit per GPU. An InfiniBand system can deliver 400 gigabit per NIC today. We can connect X7. But now let's look at what the AI people are doing that actually build specialized machines. The Google TPU from 2021, like last year, 2 years ago, oh my God, has 1 terabit per second. AWS Trainium, 1.6 terabit per second. DGX2, if you count the NVLink, 4.8 terabit per second. The Tesla Dojo chip was originally announced with a whopping 128 terabit per second. Since then, they kind of backpedaled because, yeah, that's a lot. And if you compare this to a network switch today, a network switch, Tomahawk 5 or the NVIDIA Spectrum 4, has only 51.2 terabit per second. So now this guy is telling me that an AI accelerator has more network bandwidth than a network switch? Yes, because it needs more network bandwidth than a network switch if it's fast. So that is an interesting observation, okay? So performance models indicate even higher network demand if we go to massive transformers, MOEs, sparsity, and I have another talk on sparsity on YouTube that's 4 hours long in case you want to learn everything about that. Yeah, I can talk forever, you know. If Hussein is not shoving me off the stage, I will just keep going the whole day. But then this requires even more bandwidth. So the next generation AI systems will have more bandwidth. And what are we seeing today? Our sad HPC systems already have 640 times less bandwidth than was originally announced for Dojo. Dojo is now something about 60 or 70 in the latest revision, so it's like 300 times less, but still 300 times less. So our poor AI system will be entangled in cables, essentially. By the way, that is generated by a generative AI system. Now, if we look at the cost of a fat tree, to build a 1.6T accelerator for an AWS Trainium-like system with 16,000 nodes, we would be paying about $680 million. That's most of our billion we were willing to invest just for the network. We don't even have a single piece of memory or a single piece of compute. It's just the network bandwidth we would need. That's crazy. So basically, conventional HPC networks will not fly. Topologies. Technologies will actually fly. I'll get to this at the end. So now let's see what we could do. We could actually co-design an AI supercomputer to the network properties I just described, the 3D torus. Because the 3D torus is not a fat tree. Actually, if I embed a 3D torus into a fat tree, I would be wasting about 90% of my links. So let's get rid of those links. Let's actually build a little topology that is optimized for AI. So what can we do? Well, let's say we have an accelerator package, like a GPU, okay? And now to this GPU, we are adding links. And we are adding 4 links, north, east, south, and west, just in a 2-dimensional configuration. And we add a little switch in the middle. And then we add more of those links, multiple planes. So if each of those links is 400 gigabit, you will see about 1.6 T connectivity at this device here. Now we can take these accelerators, put them on a board, on a 2x2 board. And now we can take these boards and put them in a larger topology. And what we do is, you can see here, it's a 2D arrangement on a board, which has fixed connections here. And you have a larger topology, but now each row in this larger topology is fully connected in the x direction and fully connected in the y direction. If you're a mathematician, you will immediately see, oh, that is a Hamming graph. That is a mesh, 2-dimensional mesh. That is a Hamming graph. So it's really a mesh, a Hamming graph of meshes. This is why we call the thing Hamming mesh. So what you could go, and you find the link down here, there was a paper at SC last year, you could now also build 4x4 boards. You could build larger meshes. What is nice about this is that these links on the board, they're literally PCB traces. They are free. If you know anything about networking today, most of the cost in the network is in the links, is in the cables and the transceivers. The switch is also nearly free today. It's like 20% of my cost. The moment I attach all these fiber cables, I'm going through the roof with my cost. CPO will slightly change that game, but we can talk about that offline. So now all of these onboard links are essentially free, and they give us a lot of free connectivity for this large board. Only these global links cost me, but now we have much less global link. So somehow what this topology gives us is a bandwidth cost flexibility trade-off. A global fat tree is logically fully connected. A local topology like Google has been building for the TPU. So TPU V1 used to be a 2-dimensional torus. This is how they could afford the terabit connectivity in 2021, right? They couldn't have afforded a fat tree. They just built a local connected thing. It's a 3D torus beginning from V2 or V3. I'm not 100% sure. The Hamming mesh is somewhere in between, right? So it is a fat tree. You could also call it a fat tree of tori. And yeah, now you can adjust it. You can adjust the bandwidth trade-off, the global bandwidth trade-off, flexibility, injection bandwidth, everything. I don't want to go into too much detail. I could now do a whole lot of math, giving you bisection bandwidth calculations. I could give you an exact equation for the diameter. I could give you an exact cost model. By the way, the cost model you see here, we assume switches that are about 14 grand, and cables are about 600 grand. Now multiply that by 64 because it's a 64-port switch. You already see that the cables are more expensive than the switch itself, right? And then you can also, of course, go direct attached copper cables, but they only get you about 5 meters, so that's not great. So then we have various topologies, and I just want to give you the numbers because I'm slowly running out of time. For a large accelerator cluster, if we look at the non-blocking fat tree, it's 680 million. There are lots of other topologies here as well, but let me just focus on the HX4 mesh, which is more than 10 times cheaper, only 43 million. It's still in the double-digit million, of course, right? So no question. That thing, we go down from nearly 100% global bandwidth to only 10% global bandwidth. But remember, a 3-dimensional torus does not need global bandwidth, so that may be the good idea. And even the global bandwidth per byte is about 1.7x cheaper on that topology than a fat tree. That's an unexpected observation. The all-reduction bandwidth, like the reductions I mentioned, these rings, is 99% for the fat tree and 92% for the Hamming mesh too. This is full system simulation, by the way. And here we are 14.5 times more cost-effective than the fat tree. Right? So that just as an overview. You can use this thing in practice. I don't want to go into too much detail. We have a lot of ideas how to map this. We have a lot of ideas how to make this fault tolerant. It's actually quite nice. You can map jobs to different rows and columns, because remember, these are fully connected and these are fully connected. If you have lots of failures, you can map jobs extremely flexibly. You can split them in both dimensions, and you will still have a system that looks exactly like a subcube or a subtorus out of your Hamming mesh. This is where the flexibility comes from. Google, or if you build a normal torus network, does not have that flexibility. But again, I don't have enough time to explain this. We have a lot of allocation simulations, so just believe me, you get an extremely high utilization for an average job mix that comes from an Alibaba workload, more than 90% utilization, so pretty much the same as a fat tree would be getting you. Okay, you can also see very fast all-to-all performance. I mean, very fast. The fat tree, of course, rules the game, and then Hamming mesh is relatively slow but very cost-effective. Right? This is expected for all-to-all. All reduce, we basically see very close performance to the fat tree. Right? So this is the fat tree here, and this is Hamming mesh topology I just talked about on 16,000 nodes. And again, it reaches a near peak. There are some small issues with the routing that we can talk about offline that get you a little bit of a loss here. But remember, it's about 15 times as cost effective as the other topology. So now we can also run full deep neural networks on that thing. And again, this is a relative cost savings plot. So we see something here between 1.0, so it cuts even for some configuration of ResNet. That's the minimum we get, up to 10 times more cost effective for overall system cost in that configuration. But now, actually, Brian asked me to extend my talk to talk about another slightly more recent work that I've been doing, looking at issues with Rocky. So this is why I was moving a little bit faster through the first part of the talk. But now I want to make a couple of predictions for the future. Yes, you have a question.
Could you please go back?
Of course.
Yeah. Exactly. What do you can see Slim Fly would fit here?
We actually, did we have SlimFly in the simulations? Oh no, it gets complicated. There's a lot of animations here. No, let me just skip this. Oh no, I made a mistake. Ooh. Okay, yeah, my laptop is too slow. So SlimFly would be faster, would be more cost effective. It's never faster than the fat tree. It would be more cost effective than the fat tree by about a factor of 2, right? Not the factor of 14. So that because SlimFly gives you full global bandwidth. And these deep neural networks, they don't necessarily need full global bandwidth. And so we, again, have a certain over-provisioning in this network going on. And really the observation of this talk is that these deep neural networks, they can actually live with much less global bandwidth. And so SlimFly is an interesting idea there, gets you much more cost effectiveness, but still may be over-provisioned. Okay. So now let me get to a couple of predictions. And I heard that there will be a panel today on the future of HPC, so I'll just take this up front. Prediction number 1, networks will converge. The reason is that the cloud is in a humongous gravity well that HPC will have to follow, meaning that if the cloud vendors decide they need a high-performance interconnect, they will make a high-performance interconnect. And they will make one that is much bigger than the HPC high-performance interconnect market-wise, investment-wise. And pretty much what I just talked about for the last, if you haven't been asleep, there is a very high incentive for the cloud providers to make an interconnect. Right? And we discovered this early on in about 2020, basically after my sabbatical with Microsoft, realized, oh, well, that's actually a huge market. We wrote a paper to predict this. The convergence of hyperscale data centers and high-performance computing networks appeared in 21 in IEEE Computer. We also benchmarked cloud HPC versus on-prem HPC and basically found that these networks are very much the same. And the trick here is that actually many of these cloud HPC networks, like Azure and Oracle, they're just simply deploying standard InfiniBand today. So you just buy the same network that you have in your on-prem. The two exceptions here, AWS and GCP, they use standard Ethernet. They're still somewhat competitive, but you can see significantly slower in terms of bandwidth and latency here, a factor of 10 nearly. But I would expect that those networks are going to converge. And most of the data center providers today, if they use RDMA, they use so-called Rocky RDMA, RDMA over converged Ethernet, because they're still stuck in last century in Ethernet technologies that have been traditionally used in the data center. And now the question is, are these Ethernet technologies suitable for the next generation? So let me actually use my last minutes for this presentation to talk a little bit about that. So what is RoCE, this RDMA over converged Ethernet, and what are the issues to move RoCE, if we wanted to move it, to a hyperscaler data center? So, by the way, there was an archive paper that you can find here that I and some industry friends wrote. Then Next Platform had an article on it that had a very funny title. I just have to, Luminaries argue for the interconnect we could have already had. Okay, so apparently if we would have come out earlier with that, we could have had a better interconnect today, but we shall see. So what are the problems with RoCE? So RoCE basically runs on standard Ethernet, and in order to make it run, it really just used literally the InfiniBand-based transport header and just slapped it on top of an UDP IP header. At the beginning, it slapped it on top of a what's it called? Ethernet frame that was RoCE v1. Then the data center providers didn't like that because they like IP routing. Then RoCE added in about 2014 more headers to enable IP routing, the old infrastructure. And then the problem was old InfiniBand had used a mechanism that was called go back and retransmission that could not really, or still cannot really, deal with the fact that you may have packet loss in the network. So if you run InfiniBand today or RoCE today over a lossy network, it's a recipe for disaster. What the people invented at the time was priority flow control, which is basically introducing lossless networking to Ethernet, very similar to credit-based flow control in Ethernet, but the other way around. It has all the same problems somehow, but it's the other way around. Instead of getting credits for the next link, you're pushing back. And I can go into much detail. I can give a 1-hour talk, but again, I'm running out of time. And the problem with both of those schemes is PFC as well as credit-based flow control is that you need to have enough buffering to cover your latency of the link. And that gets to be a problem, because if you're looking at the switch throughput you have, I mean, as I mentioned, today we have 51.2 terabit per second switches. Tomorrow we'll have 100 terabit per second switches. There's some kind of Moore's law-like growth going on in the switches that every couple of months, every 2 years in this case, the switch bandwidth doubles. Also, the required buffer size doubles this way. And buffers are expensive. Data is most expensive on chip. So today already we have chips with buffers with multiple megabytes of buffering. It gets worse if you're a mega data center provider, because this just assumes a 600 nanosecond traversal latency. This assumes intra-data center cables, no longer than 150 meters. If I'm now a mega data center provider, I have 2 locations, I sell you a product that says that if data center A burns down, your data is still in data center B, I need to live replicate this data. Actually, most data center providers give you such a guarantee for enough money, meaning that I need to run these protocols over long links, over regional links, 400-kilometer links, where I have latencies of 2 milliseconds. If you're looking at this, we need about 1 gigabyte of buffering if I have an 800G link. Bad. A gigabyte of buffering is bad because you literally need that buffering in SRAM. So keep that in mind. There is a problem here. Furthermore, with this whole lossless networking, there's a problem of these victim flows, which is a very old topic. We've heard about this many times. Just to recap this a little bit, is that if you basically have a communication from sender 1 to target 1 going through 2 relay switches, that is great, but now if target 1 has an incast of 4, basically means that it's giving 1/4 of its incoming bandwidth to this lower red flow, which means PFC is going to regulate the sender down to 1/4 on this link. And now what we may have is another link, another connection that could be sending at 3/4 of the bandwidth, but unfortunately, due to head-of-line buffering effects, this will only send at 1/2 of the, 1/4 of the bandwidth. This link in the middle will only be utilized 50% because of the 1/2 PFC. So most of us know this. Go back and retransmission is a problem. I talked about this before. In the data center, I have a huge problem with congestion control and co-located traffic with RoCE. RoCE is a very aggressive protocol due to its very simple congestion management. It can actually dial down other traffics quite a bit. If I have normal TCP traffic on my network, may not be the best idea. People have invented, by the way, lots of techniques here, DCQCN in collaboration with Mellanox, Timely, HPCC from Baidu, lots of stuff going on. Header sizes are a bit of a disaster. We don't really support smart stacks. Smart stacks, I mean, in network computation. Here I stole a slide from Gilad from 2020 in, I believe, SIGCOMM. where Gilad makes the point, and it's a little bit too small, I apologize, look much larger, that Rocky is actually significantly slower than InfiniBand, and which is itself significantly slower than InfiniBand Sharp accelerated for deep learning style workloads or reduced workloads. You can see here that's the InfiniBand, that's the Rocky line, lower is better, and this is the, I apologize, that's the InfiniBand Sharp line, yes, and the green one is the Rocky line. So Rocky is quite at a disadvantage here. And furthermore, Rocky has a lot of security issues in today's NICs. So there is another talk of mine on YouTube in case you want to watch another hour on simply security issues, how RDMA is broken in the data center, how you can hack your neighbors in your data center. That's also available. Then there's a latency. One interesting thing that happens in the development of Ethernet, if you look at the Ethernet roadmap by the IEEE, Ethernet is getting faster and faster and faster and faster, but it's at the same time getting slower and slower and slower because the latency is going up. With the higher bandwidth links, we will have higher latency FECs. It's a huge disaster. Catch me offline if you care about this. This would be looking at this. Let me just skip that part, and let me just skip the other predictions because I'm really running out of time. But that's fine because they were supposed to be skipped, or they were designed to be skipped. And I just want to conclude. What happened? Yes, I could give a whole lot of more predictions, but conclusions is really, we run supercomputers, or modern AI is powered by supercomputers. The communication characteristics are quite peculiar. We can actually build systems based on those communication characteristics. We can build topologies. Also, I would say that network technologies are going to converge, and they give you some reasons why we should probably revamp Rocky a bit in order to make it work for the data center for the next generation system. So with that, I would like to end my talk, and I have a lot of negative time for questions. Thank you. maybe pass on the mic.
What was that?
It's a wireless
one
network.
Okay.
Thank you, Torsten. So your talk focused on architectures for machine learning specifically. If that were your target market entirely, forgetting about deterministic 64-bit scientific computing, how would you design products differently for the one versus the other?
That is an excellent question. I get this question more often than you may think. I have a split view on this. So the split view is if we would be designing networks or technologies based on what we know today about deep learning, we would be building a network that has a very high latency, because latency costs you, and latency doesn't really matter for many of these workloads, especially in training. An extremely high bandwidth, so you would trade off latency for bandwidth, and be as cheap as possible with the very limited connectivity I told you about. Like, this is what I would build today if I would be building a network for the models that were developed in the past, the models that I can assess today. The one problem here is that transformer models that have been revolutionizing humanity, I would say, actually, it's like everything will change based on these models, didn't exist 5 years ago. Oh, maybe 6 now. But they didn't exist. We didn't even know they were coming. If you ask me today how to design a network, your semiconductor supply chain and manufacturing chain will take at least 5 years if we design it today. I have no freaking clue what's going on in 5 years, because literally 5 years ago, we didn't know about transformers. Well, 6 years, I'm exaggerating, but that is my problem. Workload is shifting incredibly fast in this field. This field is still at its infancy. We are going to see all kinds of revolutions in the next 2 to 3 years. What I would build, if I would be trading off this risk of building the wrong thing, because there are many, many startups that started all these AI startups, they started pre-transformers and they fell flat on their face when transformers came. Because the whole assumption, they made an assumption on CNNs. These assumptions are completely false for transformers, for large language models. So I don't want to make these assumptions again, right? If I would be hedging my bet, I would be building an HPC network. I would really be building an HPC network, not with full global bandwidth, with a little bit less a tapered HPC network, but I would be building for low latency, for good trade-off between latency and bandwidth. And this is a discussion I'm having actually with many vendors these days. so I'm split on this. It really depends what your design goal is, how much risk you're willing to take. Yes, there's a question back there if we still have time. And Hussein gets some steps in.
Yeah.
Thanks. Thanks for your talk. Very, very interesting talk. And so again, it's a related point. I mean, there are HPC workloads, for example, lattice QCD calculations, which map very well to a 3D torus as well for the network. So would the best approach be essentially don't consider HPC and AI as two different things, just have our scientific workflows include AI as one or more of those workflows, and then pair it up with the right other workloads as you do it. So you can target your HPC system on workflows, just include AI in that mix.
Absolutely. The answer is a very clear yes from my view, and this is why I wrote this paper on convergence, right? So I believe these are converging. If you ask me about the fundamental computation, in the network, the requirements are very, very similar. I mean, network at the end just moves data. But if you ask me about the fundamental differences on the computation side, if you're building an accelerator or even an in-network compute device, there they differ slightly. So for deep learning, you need small block data types in the future. So small is very important, so int4 and int8 and stuff like nobody would be using in scientific computing, and sparsity. So you would need support for structured sparsity in these units to get the required performance. In scientific computing, we do not understand yet how to use small data types well, and we do not understand yet how to use structured sparsity. But as soon as somebody throws them over the fence, everybody will try to figure out how to use them. And I see a lot of opportunity to actually achieve breakthroughs. And again, these markets are converging. I believe that AI is going to be the main driver. It is, as usual, scientific computing kind of tags on. Remember the good old days when it was tagging on the GPUs, like, oh, there's a gaming market, and we kind of follow that gaming market. Then it developed its own thing with the Tesla business. And now the Tesla business launched the AI revolution. Actually pretty cool if you think about it, right? And then in the even older days, like the vector processors, oh, that's also graphics units, basically. So I think something similar will happen just with AI.
Couple of remarks, if I may. One thing is that definitely in deep learning, there are two main network-related operations that are critical are all reduce and all dual. So it requires a nice, not just bandwidth, but you need to look on effective bandwidth at load and at scale. And the second one is latency is critical. So once you go to large scale, and we can discuss offline, a lot of data from DL simulators that actually show the effect of latency when you go to large scale systems. You know, you mentioned 16K GPUs, and 16K GPUs is going to become small systems, as you know, we're seeing what's happening now. So you go to much larger, and people start talking about hundreds of thousands of GPUs in a system. So both things are critical, all dual operations and all reduced operations, and therefore you do need the low latency, and you do need effective bandwidth at scale. Related to cost, definitely, you know, cost of fiber is increasing, no doubt about that, and that's one of the major parts. The network cost of the entire system is still the smaller part. Now, when you're talking about a system of, let's say, for fun, you know, $1 billion, if you build a large AI system, every percentage of performance count. So if you look on different topologies, and you say, well, you know, on one side I can build something that costs less because I need less length of cables. On the other side, a fat-tree topology that actually give me ability to do non-blocking bandwidth in that sense. If that's going to give me 10% more on a $1 billion, then the difference here doesn't actually make sense to look on any other topology, because if you take even any other topology for free, it might not be good enough actually to cover the 10% of $1 billion. So there's just, you know, things to think about. Related to RDMA, RDMA not necessarily ties to network latencies in a sense, right? RDMA was meant to do to be able to move data directly to the host memory or GPU memory, right? The remote direct memory access. Yeah. Latency of ROCE determined by the latency of the switches and the NICs and what's happening on the network, not actually related to ROCE itself or related to RDMA. And you probably don't run RDMA over 400 kilometers of distance, right? You stay within the data center doesn't go to 400 kilometers. So we need to look on much smaller distances when you build an AI platform.
An AI platform, yes, but I didn't say AI for the ROCE part.
Yeah, but if we want to use ROCE, I want to use ROCE within the AI data center, not necessarily I want to run ROCE over 400 kilometers.
There's at least one big mega data center provider that uses ROCE for storage.
The things you can do that. By the way, there are appliances that actually enable you to do that, but they're actually built in order to make it work. And one last thing also to think about. When we look on Ethernet, for example, not every Ethernet is the same Ethernet. Meaning if you look on different kind of switches that exist out there, there are switches that were built for cloud infrastructure, there are switches that are built for telco, there are switches that are built for enterprise. There is no one Ethernet fits all. Now when we talk about converged networks, the question is converged network to what purpose? Because if I'm building a cloud service network, I don't need to deal with the same things that I'm building something else. Because here I can have, you know, long tail, it's fine, you know, it's a cloud services and stuff like that. It's not the same as building a compute network, for example. So You probably may see converge in some areas, but still there is different workloads that require different kind of components, and then you might build different things. But today there is no one Ethernet fits all. That's why you have different Silicon devices on Ethernet switches and so forth. That was a long, sorry.
Okay, well, no, yeah, next time you should give the talk. But let me rebut. So all-to-all is an important workload, but only on a very small scale. So meaning in mixture of experts, it is used mostly for mixture of experts. There are no more than 128 experts in practice today. So meaning you have a lot of all-to-alls going on in parallel in groups of 128. They don't need global bandwidth. So that's basically the same thing. You could now argue that Facebook runs DLRM at very high scale, where you need some all-to-all V, in fact. That all-to-all V is smaller than the BDP, so you basically just flood all your switch buffers. So that is a special case, I would say. But I didn't consider DLRM here. For DLRM, I would give you the point. Then on the convergence, that's an interesting, that's where we have different companies having very different philosophies. So Google is running workloads, HPC workloads on the front-end network, Amazon as well. Amazon is running training workloads on the front-end network. So you could now argue that they don't know what they're doing, sure. Microsoft, Oracle, and Facebook is running in back-end networks pretty much. Sure, that is just different views. But now the fundamental question is, do you want to invest in two networks, right? Do you want to have a front-end network to just run your thing and a back-end network, or do you want to have one converged network? Or do you always want to have two different kinds of nodes for your workloads? Do you never want to share microservices? We'll see. And I completely agree with you. There is Ethernet and Ethernet. Yes. There's like low latency switches. There's high latency switches. There are cheap switches. There are expensive switches. If you just look at Broadcom, the Tomahawk versus Jericho line, like extremely different. Running RDMA over long distance links, that is actually done in industry in practice. Unfortunately, I think it's a bad idea, but people do this with humongous Jericho switches. And it's not AI. It's absolutely not AI. It's storage. That's true. Yeah. So maybe I confused that. Yes. But second, it may not have been clear. The last part was really more about Rocky in general, not Rocky in the context of AI. That's a very good point. Cool.
So I think I have like maybe one question for you, and that's going to be very quite short, and especially related to this. You know, we have been talking a lot about conversion between cloud and HPC for like the last 2-3 years. Many companies, that's including NVIDIA and others, they have been taking the AI as important as HPC, and they were driving it. In every event, it's been like presented with AI. So what do you think about research centers that they are not taking AI still in consideration? There are many examples, actually, though I'm not going to name any. So what these research centers should take in consideration? Are we expecting to see conversion between HPC and AI, or the AI will be driving the HPC future?
Yeah, that's an interesting question. Going back to the previous answer, I hope they would converge, but I would somewhat expect that AI is such a strong pull. If you just look at what's happening, and actually I did have a slide on this specifically, if we still have like 30 seconds for me to get there, these accelerators. So here is Lisa Su talking about 30 times more efficient FP8 performance than FP64. Here's Jensen pointing at a data sheet that was ISSCC. No, it's 3 weeks ago. Sorry, I didn't update that slide. Here's Jensen pointing at actually already having this implemented in Hopper. So we are talking about 30 times performance benefit if I'm going down a factor of 8 in precision, in bits precision. So somehow what this means, there will be an incredible pressure coming to use these low precision data types, and if somebody optimizes for deep learning, there will be more FP8 and less FP64, because you only have limited chip space. So I'm expecting that this market will just be such a heavy pull that we will have to follow as an HPC field. And the research centers will have to follow. They may just be a little bit late, but they probably have to follow. It's just a market size argument.
Cool. Thank you.
Thank you.
Thank you, Torsten.
You bet. Thank you.
I'm not going to introduce Gilad. I believe it's.
Then ask.
So Gilad is going to talk about our DPUs, I believe. Yeah, offloading services.
Is that what he's going to be talking about?
Yeah.
Fantastic.
So, yeah.
Now you have 30 minutes.
Thanks. Yeah, you know, I'm beside of enjoying the time with the HPC Council. I do relate it to NVIDIA. And since we missed the speaker from NVIDIA that was supposed to be here, I was asked to present, so I'll do that. Even though I typically don't stand here without Hussein, but Hussein just escaped. Okay, so we'll talk about DPUs. I wanted to talk with you about DPUs. What we're doing with DPUs, and feel free to ask questions and just stop me throughout. So just oh, there is too much light. Can you guys see that? Meaning I can, but I have a different monitor. Okay, so I'm not going to go, I'm going to focus on the technology side, but just to give a full map. From networking perspective, NVIDIA actually building or developing today two different kind of networks. One of them is the InfiniBand network, which covers by the Quantum 2 switch with the combinations of ConnectX or Bluefield, the data processing unit. Ethernet with Spectrum 4, which also utilized Bluefield DPU, and ConnectX, which those devices can run both InfiniBand and Ethernet, as well as NVLink that is being used for GPU to GPU connectivity. And in many systems, we're actually leveraging all three. So we're using NVLink to connect between GPUs, and the number can change, depends on the workload and the model size. And then connectivity can be either InfiniBand or Ethernet. Depends on what you want to build and what you want to achieve. I'm going to focus more on the combination of the InfiniBand network with data processing unit and what can be done there. The strength of InfiniBand comes from its main fundamentals. Definitely, a network is not being defined by the packet format. So the packet format of InfiniBand doesn't make it different than the packet format of Ethernet. But the big question is how you manage the network and how you build that network. There are three elements within InfiniBand that makes them one of the most used or leading technology for HPC. First one is in-network computing. In-network computing started with InfiniBand multiple years ago with the motivations to run data algorithms on the network itself when you move data. One of the examples, key example is doing data reductions on a switch network. So in that case, instead of doing data reductions on endpoints and the need to exchange data between endpoints in order to do the data reduction operations, you can just do that on a switch fabric. You send data to the switch, all the nodes send the data to the switch does the data reduction and does broadcast back to all of the endpoints. That actually enables to save half of the bandwidth for data reduction operations. Doing all reduce on the node will require us to send 2x the amount of bandwidth, 2x the amount of data throughout the network, comparing to just doing data reductions on the switches. Second one is it's InfiniBand. It's a very simple protocol, extremely simple protocol. It's a flat network, and because of that, you can actually build any sort of topology and use the same building block to build any scale, any size. It doesn't have the notions of top of rack and aggregation layer and stuff like that. It's just the same component, same device, and you can build any size of infrastructure. The third one is that InfiniBand was created as a software-defined network. Pure software-defined network before actually people knew what SDN is. That means that you can control the entire routing from a single place. You can have different routing schemes. You can do fine-grained adaptive routing today and stuff like that. So taking those capabilities and then taking the DPU also into the game, and we'll talk about the DPU in a couple of slides. We were working to try and overcome some of the performance bottlenecks for HPC that actually exist because of running MPI on the node, because of running MPI on the CPU. The first one is trying to achieve overlapping between compute and communication. And for doing that, you need to have a different compute device that can run MPI and run communications, and a different compute device that can run compute. Now, non-blocking MPI operations exist in the MPI spec for like 20 years, give or take, more or less. And no one to date actually managed to take advantage of them. There were a lot of experiments and papers trying to take CPUs and break down some of the cores of the CPU to run MPI and the rest of the cores to run compute. But that actually led to reduction in application performance because you create different kind of bottlenecks. For example, the different cores that are running MPI are consuming the part of the memory I/O that is required for the other cores that are running compute. So you actually cannot do that on a CPU. And it really doesn't make sense to spend an entire CPU just doing MPI. So that's why people were not able to use or leverage from overlapping. Second one is load imbalance. We all know issues of slow nodes, and a slow node will determine the performance of the entire system on the entire application. And the reason is that, obviously, if you're starting to run a synchronization, MPI synchronization, and you have one node that is not ready, it's going to delay the entire work or the entire communication process. If we have another device that can progress MPI operations, even though the CPUs are still busy, then we can reduce from that effect. So that's another thing that we can leverage in network computing to reduce the issues of load imbalance. The third one is jitter, and the effect of system noise and jitter on applications is well known. So moving out the sensitive operations to a device that doesn't suffer from system noise and jitter will definitely improve performance. And the last one was what happened in a system that's running multiple jobs. System that runs single job, that's great, because that single jobs will provide the same performance over and over again when you're running it. But when you're dealing with a multi-job environment or a multi-tenant environment, there's a lot of cases that one job can impact another job performance. So we want to provide isolation, not just isolation within the node, for example, but you want to do isolation within the network between jobs that are sharing the same quality of service. And for that cases, you want to make sure that one job will not impact another job performance. So those were the four bottlenecks that we were dealing with, and with the DPU, we were able to actually overcome those or reduce the negative effect of them. There are a lot of computing in the network today, a lot of in-network computing. The switches are able to do large message and small message reductions in hardware. And they can support multiple concurrent large message reduction trees at the same time. So that's something that is being heavily used for both in AI and obviously traditional HPC. On the NIC and the DPU, there are specific hardware for in-network computing, such as elements to accelerate small message all-to-all operations and ability to accelerate tag matching operations. And the DPU actually brings also programmability into the network. So be able to actually move more operations and more work into the network itself. So first, just looking on the effect of the data reductions that runs on the switches. Here you can see nickel or reduced performance, comparing different kind of system sizes. The dashed lines demonstrating performance of all reduced in nickel when you're running everything on the host, not using the data reductions on the switches. The more GPUs you have, or the bigger the system is, it takes more time to actually get to higher bandwidth. The solid lines, this is all reduced bandwidth when you're running reductions on the switches. So regardless of the system size, doing reductions on the switches gives you full wire speed, full bandwidth at every capacity, and you're getting to almost a 2x advantage, to almost 2x performance advantage, comparing to running reductions on an endpoint, and you choose which algorithm you want to use. So that's the importance of Sharp, and that's why doing reductions of the switches has become a very important thing for AI and DL workloads. So going to the DPU, what is a data processing unit? A data processing unit first is a NIC. So a DPU replaces the NIC and provides the full NIC functionality. The latest Connect X7 functionality, which is a NIC that runs at 400 gigabit per second speed with PCI Express Gen 5 interface, exists within the latest DPU, which is called Bluefield 3, which is now sampling out. Beyond of that, Bluefield also include two programmable engines. One is an array of 16 ARM cores that are actually running Linux. So you're running Linux within a NIC or within a data processing unit, and actually that data processing unit becomes another computer that you put inside of your computer. There is another 16-core data path accelerator that runs in parallel to be able to do quick things on the data as it moves in and out. So there is a Linux machine within that NIC that run Linux, and you can do multiple operations. You can inject data to the network. You can process data that comes from the network. You can move data directly to the host memory locally and remotely, completely bypassing the CPU. So you can do full operations on that device. And there is also a data path accelerator, so you can actually change data or change packets, data in the packets when they go in and out, or even generate data into the network in a much faster way. So what we're doing with DPUs. So first, the DPU, one of the applications for the DPU is the infrastructure workload. And from that reason, we see that majority of the cloud providers out there are actually moving to use DPUs. Amazon network, it's actually a DPU. They designed their own DPU and they're running DPUs. Others are using merchant DPUs or working to creating their own and so forth. But essentially, DPUs, one of the main applications of the DPUs was to run the infrastructure. And the reason for that is that the infrastructure workloads become very, very complex. We're building larger systems. There are more tenants in the cloud environments. Hypervisors becomes much more complicated. And running hypervisors on a CPU is going to take a lot of CPU resources. You want to use those resources for supporting or for running guest OSs or running users. Second reason is security. On the infrastructure domain. Running the hypervisor and the applications on the same compute platform is a security threat. If a malicious user gets access to the CPU, get access to the hypervisor, you can control the entire system. So in order to overcome that security threat, you want to separate between the infrastructure domain and the application domain. So that's another reason that you need another computing engine or compute engine to run the hypervisor to reduce the overhead and to improve security. Now the DPU in that case, the ARM cores are not faster than the host CPU, but the DPU strength is not just having those ARM cores, but also having dedicated hardware engines for the infrastructure. Engines like encryptions and decryptions, engines like doing isolations and so forth, that makes that a great infrastructure processor. So that is one of the main applications. The second one is storage. DPU also include the element of doing compressions and decompressions and checksums and NVMe over fabrics and so forth, which makes the DPU a great storage processor as well. And the third application, it's using DPU as an MPI processor or communication framework processor. And using the DPU as an MPI processor enable us actually to achieve overlapping for the first time, real overlapping between compute and communication, to reduce load imbalance issues and all the other bottlenecks that I mentioned before. The way that we use the DPU is with software development kit and runtime that's called Doka, something that NVIDIA created. If you know CUDA for GPUs, it's the same like Doka for DPUs. Doka is an SDK and a runtime that enables to put services on the DPU and expose those services to application running on the host. We have been adding services for doing point-to-point and collective operations on the DPU with UCC and UCX. There is also storage services and other services and so forth to cover the other workloads that the DPU is supporting. UCC and UCX enables us to run HPCX MPI over the DPU. DK presented yesterday and is going to have another session, I think, talking about MVAPIC running on the DPU. And I believe that OSU will have a service that runs on the DPU, taking that into production systems. OpenMPI, MPIC, and so forth, they all are able to run on the DPU. So what are the performance numbers that we're seeing by moving MPI to the DPU? So I have some examples here. I'm sure that DK will show more examples on MVAPIC, but this is looking at all-to-all V latency. And this is blocking all-to-all V latency. On the left side, it's one ppn. On the right side, it's full ppn. So we're seeing that getting to 60 nodes, there is a nice performance increase or reduction in latency. Going to 32 nodes, we're getting almost to half of the latency. Running MPI operations on a DPU. Going to non-blocking all-to-all V performance, you can see that the impact starts at 4 nodes. A small, very small system. 60 nodes, it's much less than half of the latency there. So there is a good impact on latency and of course enabling overlapping. Again, 1 ppn versus full ppn. Running MPI on the DPU enables you to get 100% overlapping, and it doesn't reduce from the host CPU, memory I/O, and other issues that happen when we use the CPU trying to do overlapping. Now, those just MPI performance data. It doesn't take into consideration what happened and load imbalancing issues and jitter and so forth. But those elements are getting together when we're looking on the entire application performance. The first application that was run utilizing the DPU, because it was a simple one, was FFT, or the 3-dimensional FFT. That was mainly utilizing all-to-all operations. That FFT was modified to use non-blocking all-to-all operations, and with that got to 1.26x performance improvement. The next example was GSM. This is application from JMA, which is the Weather Institute in Japan, and moving GSM to leverage the DPU, running MPI on the DPU, got more than 1.2x. And recently we've tested Octopus, which is a physics chemistry code from Max Planck Institute. It was more than 1.2x performance improvement. We are creating more examples, by the way, of more workloads in different areas. Workloads that don't really use much of MPI, we're seeing around 1.1 performance improvement. Workloads that do use MPI nicely, such as the examples here, we're seeing more than 1.2x performance improvement. So that's a good acceleration. That's a good performance acceleration, and it helps to reduce multiple bottlenecks that we could not actually deal with them before, just running MPI on the host. Another item is performance isolation, which I mentioned before. Performance isolation means that, again, in a multi-job environment, you want to make sure that one job cannot impact the other job performance. And this is where the DPU can actually make things very, very nice. You can see an experiment here that we have done and presented, and that was done on a 400 nodes. Actually, we went into work together with Microsoft to do that demonstration. So what you see here is that works. Never mind. What you see is an example of running several codes. So the one in the upper part, we took lamps. We took lamps as an example. You can pick any other scientific code, but we took lamps. On the left side, the upper left side, you can see a graph with a kind of blue line, or blue histograms in a sense. What we did on the left is just running lamps over part of the system that we had, and we did it over and over and over again. And every time we kind of mark the performance data, the performance results of lamps, and essentially we got the same number over and over again. So that's why you see a histogram that it's very, very narrow. In the middle, in the upper middle graph, in this case we continue to run lamps, but now on the rest of the nodes we just run other workloads. We did some other scientific workloads, we did some storage workloads, some good all-to-all operations and so forth. And now we stopped getting the same performance over and over again for lamps. Sometimes it was a nice performance, sometimes it was 2x worse. So that demonstrates the impact of other jobs on our jobs that is running on a system. On the right upper corner, this is what we able to achieve when running performance isolations on the network. And you see the green line, and there is a dash blue line. The dash blue line is actually copying of the results on the left side, just running lamps by itself, and the green showing the results of lamps running in the multi-job environment. And essentially, we're getting the same performance. So, and the lower part, it's doing the same experiments with AMG, just as another workload. Now, if you're going to look on all the workloads, you're actually going to see the same thing. Now, how do we achieve performance isolation? Performance isolation is being achieved here by essentially controlling the injection rate of data to the network from every NIC perspective, and that's done per communication channel or done per queue, for example. And what you want to make sure that the injection rate, the data injection rate into the network, it's what the receiver can consume. If the receiver cannot consume what he's supposed to get, then in that case, you can create contention within the network that might impact other jobs. So you want to control the injection rate into the network based on receiver, based on communication channel, and so forth. And that was what the performance isolation is doing on the NIC, combining with information getting from the switch. Now, with the DPU improves that operations, but actually leveraging AI framework to learn the behavior of the system, to learn the conditions of the network, the topologies, and how things were done previously in order to optimize that on the existing data center. And that combination actually gives the great results that in a multi-job environment, we can ensure that every job will get the same performance as it just running by itself. So those are things around data processing units. I think we are on time, more or less. 4 minutes, 5 minutes before break. Before break? Yeah. Oh, okay. So if you want to discuss more about DPUs, happy to do that over break. If there are any questions now, happy to answer.
Any questions for Gilad?
Thank you.
All right, so we have our first break, and it's a 30-minute one, so we have coffee and other little goodies. And please talk to the sponsors that are here too as well. They have tables set up. And we'll see you back here at 11:30. Thank you.